Hello and welcome to another STEM experiment. Today we are going to be focusing on maths, and I'm going to be talking about 3D shapes. For this experiment I've done something a bit different, and I've created a PowerPoint as it will be easier to explain as I go along. So the first slide is definitions. It is important to understand the definitions first so that we know which part of the shape we're talking about. So, in terms of dimensions, we've got the length, the height, and the width. The length is the measurement of something from end to end or along its straightest line. So as you can see from this diagram here, this is the length. This is also the length. The height is the distance from the top to the bottom of something, or the quality of being tall. So this is the height. The width is the distance across something from one side to the other. So this would be the width. In terms of properties, you've got the face, so this part. You've also got the edges, so those would be the height, length and width, and you've got the vertices or the corners, the points. You've also got truncated, which means that it's got without the top or the end sections. So for example, you might have a triangle but it's missing its vertices. Or the corners, and then you've also got a snub cube, for example, which is derived from a simpler polyhedron by the addition of extra triangular faces. So on to our curved solids. Curved solids are not polyhedral because they contain at least one curved surface and therefore do not fit the definitions of a polyhedron, which is made up solely of 2D shapes or polygons that are completely flat and straight lines. The different types of curved solids are cylinder, cone, sphere and torus, as you can see here. We then move on to the platonic solids, and this gets to the history part, which I'm quite excited about as one of my degrees was in history. So in his dialogue Timaeus, Plato presents 5 special polyhedra, otherwise known as the platonic solids. These 5 polyhedral 3D shapes are defined by 2 characteristics. The first characteristic being that the faces are all the same. So for example, in a pyramid, you've got all the faces being triangles, and the same number of faces meet at each vertex. So example, going back to the pyramid, you've then got 4 of these faces. 5 solids are the cube, the tetrahedron, the octahedron, the dodecahedron, and the isosahedron. And again, I've put these into a diagram for you. This is not actually one of my diagrams. It is one that I use from a website. To see all the links that I've used throughout this PowerPoint, please refer to the bibliography that I've posted at the end. So a side note is that in Timaeus, Plato associates these 5 solids with the classical 4 elements and the cosmos, as he believed them to be the building blocks of the universe. This has got nothing related to modern day maths, of course, but is still an interesting fact. Archimedes was the next main scholar to develop geometry, which is what we're studying today. So Archimedes was a famous mathematician from ancient Italy. He revolutionized geometry in his work, in his treatise on plane equilibria. He discovered fundamental theories concerning the center of gravity of 2D shapes, and also that 3D shapes could be made up of multiple different types of polygons. So a polygon, for example, you might have this one, we've got a hexagon, but we've also got triangles. Scholars typically name 13 Archimedean solids: the truncated tetrahedron, the cuboctahedron, the truncated cube, the truncated octahedron, the rhombicubectahedron, the truncated cuboctahedron, the snub cube, the isosceles the truncated dodecahedron, the truncated isosahedron, the rhombicos dodecahedron, and the truncated isosododecahedron, and finally the snub dodecahedron. Moving on to the next slide, we've got Albrecht Dürer, who lived from 1471 to 1528, so the Renaissance period. Dürer was a German painter and printmaker and also a theorist, so not necessarily related solely to mathematics. He was, if you like, a polymath. In his book, known in English as The Course in the Art of Measurement with Compass and Ruler, he guided different sorts of craftsmen and artists and anyone basically interested in measurements by containing the world's first 3D nets. And these focus particularly on the Platonic solids and several of the Archimedean solids that I've just gone through. We still use this practice today. My challenge for you is that in the next part of the video, I've already guided you how to make a cube, but I want you to try some of these others that I've listed in the following PowerPoint slides. So this side is the Platonic solids. We've got 5 of these, and then come the 13 Archimedean solids. And finally, we've got the circular solids as well. So as I mentioned before, these are all of the resources that I've used. Welcome to the next part of the video. I am going to show you how to draw the cube net. So the cube, remember, is a Platonic solid. And for this experiment, you will need a sharp pencil, a ruler, some glue, some scissors, and a rubber. You will also need some graph paper. So I've drawn out a template of what I'm going to use, but I'm going to double that and make it bigger using some art paper. So as you can see, I folded the art paper in half lengthways, just so that I can get the middle of the page and make sure that my template is centered. And I'm going to use my ruler and measure out 3 centimeters on either side. So I'm going to put the ruler at 3, and I'm going to start as close to the top as possible, so that I've got enough room to draw the rest of the template. So starting at 0 and ending at 3 in the center, I'm going up to 6. Try and make sure that your ruler is as straight as possible, when you're doing this, because that will affect the accuracy of your cube when you come to folding it up. So I'm just going to make a little mark at the end of that, because I can see that the cube then has 3 more squares below the first cube, so there's 4 squares going down. And again, a mark at the 6 when I reach the next one, 12, 6, and that makes it easier to draw the other side as well, because you can just put the bottom of the ruler where the first line ends and then just score it off at the end. So now what I'm going to do is I can see that my template is like a cross, and I've got 2 squares on either side. So I'm just going to go down to the second square of the 4 down the middle, and starting at the bottom right hand corner, I'm going to measure out 6 centimeters. For each of the 3 sides. So now that I've drawn out my template, what I need to do is add some tabs so that I can stick the square together. So the tabs do not need to be that big. I'm going to do 1 centimeter height-wise for each of them. So all I'm doing is that I've drawn a diagonal from the corner of the cube, as you can see, and that is the tab here. So you might want to shade that in so that you can remember. And I'm just going to draw in the rest of the tabs now. Knowing where to place the tabs can be quite difficult, so you can ask a parent or guardian or even teacher to help you. There's also a lot of online resources that you can use, which actually provide the templates ready-made for you. But it's quite good to learn how to draw your own. and the final tab. Right, now that I've drawn all my tabs, I'm just going to again shade them in. It doesn't need to be precise, just a squiggly line will do, so that I can remember which side to glue later on. And your finished diagram should look something like this. All I'm going to do now is just cut out my diagram or net. Right, so cut out, it should look something like this. And what I'm going to do now is get my glue, and I'm going to turn it over and stick it, the glue on the tabs from the other side. This is to make sure that the pencil marks do not show. You may have to go over the glue once or twice, depending on how sticky it is. And what I should have done before I glued is actually fold along the pencil marks. You need to do this for the tabs as well. Right, so when you've done that, it should look something like this. And now you can start to fold it up into place. So this may take some time with the other nets because they are more complicated. I'm just using this one as an example so that anyone can do it. So as you can see, it is quite difficult to hold it in place. You may need to spend quite a lot of time holding the tabs for each one to make sure that they stick and set. But your final piece should look something like this. And that is my experiment. Thank you for watching and see you again next time. Bye!